Welcome back to the Automation Podcast. My name is Shawn Tierney, and this week on the show, I meet up with Chad Parker from IFM, who introduces us to their line of 2D vision cameras. And at the end of his presentation, he even gives us a demonstration on how to set it up in an error-proofing application. Chad, thank you for coming on the show. I'm looking forward to learning all about this new product. But before we jump into your presentation and demo, could you first introduce yourself to our audience?
Hi, Shawn. Thanks for having me. My name is Chad Parker. I am the North American Product Manager at IFM Effector. Specifically today, one of my product lines is going to be 2D cameras for error-proofing applications, and we'll get into that. Prior to IFM, I did spend some years at a custom machine builder, so I have a lot of experience with custom machinery and using lots of different product lines, including cameras.
That's awesome. Great. So what are we looking at today?
So today specifically, we're going to look at a new two-dimensional camera from IFM. The idea and the goal of the development was let's do 80% of the applications as easy and cost-effective as possible. So we want to have a user interface that's very easy to use and very easy to understand, as well as some tools on the website to develop our application to make sure that we're picking the right products before a customer would go ahead and buy. So first of all, I just wanted to take a step back and introduce the audience to who is IFM, if you haven't heard of us before. So we are a industrial automation sensor manufacturer. So we make and develop the products that we sell. And what you can see here is about the size of the company. We're a global company based in Essen, Germany, which is Northwest Germany. Of course, as mentioned, I am in the United States. The US is a very large market, and we're the #1 subsidiary. You can see an idea of our sales here. But one thing we really emphasize on, especially during these times coming through supply chain, is we put a lot of effort and investment into getting our customers a product as soon as we can at or before their expected receiving date. So we have about a 90% score on that globally. And that's something we're very proud of, that we can provide our goods and services to the customer when it's needed.
Nice. And for the audio-only audience, that's just a couple of the numbers there. I think it was 8,700 employees over that and 1.5 billion euros in sales. So pretty big numbers.
Yes. Excellent. Thanks, Shawn. So just quickly, a quick table of contents. What are we going to talk about today? So first, we're going to discuss what are these types of applications in the industry. They're known as error proofing, mistake proofing, or a lot of people you hear will say poka-yoke applications. So the product line that we're going to cover today solves these types of applications, and we're going to discuss exactly what these applications are. Second, we can go through why is it so important to find errors in a production process fast. So there's definitely advantages to catching errors as you're producing a good on a machine as soon as you can, rather than what is worst case scenario is that you ship it to a customer and it's incorrect. Third, we're going to take a look at how camera technologies work and certain things that you have to know and consider before you actually go ahead and do an application. And then at the end, I'll do a quick live demonstration with a part next to me, and we can have a little bit of fun and program our first application together. So first, we're looking at a slide of what are error-proofing applications. So I have a picture of a automated machine in the center of the page, and there's lots of different things that need to be checked. So error-proofing is just the ability to catch a mistake in the production process. One very common way to do this is to use a camera, and that's the product that we're going to be going over today. But some of these applications are, let's call them manufacturing processes that have to be completed, and then you have to check to make sure it was done correctly. For example, if you are machining a piece of metal to a certain tolerance, and that number has to be checked. If you are sorting something, if you're checking the position of a product, if something is aligned or not aligned, simple part presence. If the product has been completed, say orientation of it, or assembly of the product, making sure everything was assembled correctly. And then, of course, in the logistics world, would be track and trace. So next, I'm showing a slide of an ever-increasing graph, so an XY graph. So on the Y, we see cost to a customer or a given factory, and on the X, we can see when that error is actually discovered. So if we imagine that you have a machine in front of you, and it makes, let's say, a glove box latch inside of your car, just something that we can all understand. If that assembly is done incorrectly and we take a picture of it at the point of which it was made inside the machine, all that you have to do in the machine is kick that part out. It did not meet inspection, and then you go ahead and bring the next part in, and you miss a second of your time. No big deal. The bad part got kicked out. Everything's fine. If you didn't catch it at that point of manufacturing, you catch it at the end of the production line, then you know that everything that was made after that part has to be put into question, because we don't know if the machine is actually working or not. So if you catch it, say, after every single production step is completed and on the outside is the finished good, and you catch an error, then it becomes more expensive. And then, of course, the worst thing that can happen, and we read this in the news every day, whether it's food and beverage products or something in your car, but the worst thing that can happen is that you make parts and then you start shipping them to customers. Customers start plugging them in, and then things start failing. That is the absolute worst case scenario and can cost an unlimited amount of money in fixing it, and also in the company's reputation as well. So that's why I go back to our main reason for developing this product is we want to solve most of the applications out there, and we want to bring our price point down so that a customer can afford to have more of these checks at every assembly point in a machine, so that we can avoid sending a bad product out to a customer, which costs a completely different ballpark.
Yeah, and putting safety concerns aside, just the indigestion that the customer, I know I had purchased a car years ago, the speed sensors were installed incorrectly, and after you were driving it for a while, they'd make a big noise and then break off. There were a lot of indigestion for somebody who just bought a very expensive product to have to go through that. So if that could have been caught during production, right, before a lot of time and effort and money went into refining that speed sensor, right? Maybe when it was in the very beginning, maybe it was a bad bracket. If that could have been found, so much cost could have been saved in the whole development, and and avoid that bad customer taste, that bad customer experience at the end of the journey there. So totally understand what you're saying there.
Yeah, perfect. You got it spot on. So next, just a quick overview of the type of technologies that you would see in your average factory around the globe for these types of applications. Sometimes it could be making sure the correct code is on a box, so you have either 1D or 2D code reading. We have a 2D, what we call either vision or machine vision cameras. This is what we're going to look at today. There's also touch probes that exist out there. So these are very highly accurate, where a machine will come over and physically touch a part at different corners and make sure that it has the right dimensions. Color sensing is going to be very popular, mainly in packaging for food and beverage applications. Fiber optic sensors are also everywhere. These are very small optical devices that have the ability to be put into very small spaces and very difficult to reach spaces. And laser sensors are also very, very popular. There's two different types. There's a triangulation principle that really works on geometry to tell the distance to a target. And then there's some also time of flight principles out there. Specifically, quick plug, IFM has our own proprietary brand of time of flight that really brings the list price down. But that's maybe for another discussion. But these are some very common items that you would see in a manufacturing plant to try and catch these errors in production as early as possible. So moving on, how cameras actually work. So this is the same whether it's in your smartphone or any industrial camera that you would see anywhere in factories across the globe. But these are CMOS-based imagers. So what CMOS is really a low-cost production process. But if we look at it at its very simplest form, you have a big array of pixels. That's that would be the resolution of your smartphone or an industrial camera or anything like that. Each one of these little pixels think of it as its own little analog device. On top of these pixels is a little lens. And so when these pixels are exposed to light, you hit the button to take a picture. And then the shutter opens, and then each of these pixels will collect some light if it's there to even collect. And so what it is think of it as each pixel is its own little analog device collecting photons of light. The more light that comes in, the more that pixel is going to appear to be white, and the less that it comes in is going to appear to be black. And then, of course, every single color of gray in between. So that's just the hardware side. The only thing that really changes from one camera to the next, in the most part, and I'm simplifying this, is just going to be that resolution. So to give you an idea, the camera that we're talking about here is going to be 1.2 megapixels or 1.2 million pixels. So, but this is the basis of how the hardware actually works. So moving on top of the hardware, so imagine we now have a big array of pixels, and in our case, it's going to be from black to white. There are color imagers like you would see in your phone that is not in our device for industrial inspection, but they work the same way. So what is really kind of separates one manufacturer to the next is going to be the software that has to be used to analyze this now big picture of black through white pixels that we now have in front of us. And so these software tools are developed and they can do a lot of different things. Like they can calculate depth measurement of something by telling its light intensity as you see it on an imager. Is it very dark or is it very white? You can have distance measurement, like a picture that we show here, like a fan. Can I measure the distance between the gaps of the blades of a fan? Something else that's very common that's actually used a lot in logistics because it speeds things up, but something that's called OCR or optical character recognition. And what this does is it provides an automated way to read alphanumeric characters or any letter or any number, and then we can understand what that actually is and then compare it to make sure that the product is in the right place. And for our purpose today, we use what's called a blob tool. It's a pixel counting analysis. And all that this is really doing is you're training the camera to know what kind of colors am I interested in? Am I interested in this set of grays or am I interested in whites or blacks? The user can set whatever they want. Another one is going to be optical character verification. So just to give you an idea, this is something that's new and being developed. And in the example that I'm showing here is we have a very nice letter A, and then we have a second letter A that has like some blotches on it starting to look a little bit different than an A. And what this OCV does is it starts to characterize, is that an A or is that not an A? And then last, the second tool that I will show you today is our camera can do what is known as pattern matching, or in the industry we call it contour. So what this is doing is it's really trying to find the edges of where a black part becomes white or a white part becomes black. And so you can put this tool around an area and then grab the outside shapes of what this actually looks like. And so next, just some basics in terms of how do you actually develop an application. So let's say before you even buy anything, it's important to understand how it works, which we've reviewed. But here are some other tools, and what I'm showing here is this is information on the website. So you're just sitting down, someone presents you with a new application to do. Where do you start? So the first thing you need to understand is the field of view of the camera. You need to make sure that the camera can see the entire part that you're trying to look at. So that's very important. Working distance. So a lot of people sometimes say, I can only mount the camera in this position because there's something overhead or there's something in the way. So understanding physically where can you put the camera. The resolution that's going to be required to do the job, and then also the depth of field. The depth of field is just, it's really whenever you take a picture with your phone and you have an autofocus of your friend in front of you and someone else that could be 6 feet behind them, the depth of field would be when does the point come when both people would be clear in the picture. So these are just things that you have to be mindful of. So I gave a quick example that we could do this quickly. So let's say you have a 50 by 50 or a 1 inch by or 2 inch by 2 inch by 1 inch metal block in front of us, and there's a 2 millimeter hole that's drilled in it. If we go to a desired working distance, let's say it had to be 500 millimeters, we use a chart from our website that can tell us with a standard lens, each pixel is going to be the size of 0.12 millimeters. Since our hole is 2 millimeters, 0.12 is less than 2 millimeters. So we can use these tools to say, okay, I have more resolution than what is required for the application. I can pick this part, and I know that and I know that this hardware is going to work. So next, in terms of trying to develop an application together, The number one thing, and everyone knows this because we all take pictures, is lighting is pretty much everything when you're doing these applications. So if you have very poor lighting, because how cameras work, it's very much based on contrast. So we like to see as dark a black as we can. We like to see as white as we can because we can tell the difference very easily. As grays start coming into the picture, which they will, it's really, you can use lighting to your advantage to make sure that you're illuminating the right thing. So, for example, for those that are listening, we're looking at a king playing card. So a simple playing card, it's a king card. And what we did was we give you a picture of what it looks like under natural light, which is what it's going to look like if you're holding it in your hand. And then what it looks like with white light, red light, and infrared light. So now the white light, red light, and infrared light, it's gonna just be a monochrome image. So it's just black to white, white to black. But you'll be able to see how light affects it. So, like for example, the king is wearing a red robe. When you put red LEDs on it to illuminate the picture, that red robe appears to be white actually because it's the same color. Now, what is also interesting and most common, I would say 80% of the time in factories today, you're going to see infrared light. So infrared light you cannot see. And the main reason for that is I don't know any operators that like looking at strobing lights, and I don't know how long I could even do anything if I had a strobing red light in front of me. So that's the most common, and I just bring this up just to make sure that the audience understands that it's very important to pick the right type of light. And so next, for this is a lot easier to tell how different colors of light will affect a part. So we just are looking at pen caps of red, green, blue, and black. And then we're showing you images when we do red. The red looks very white. The rest look very dark. For green, the green looks very light. The rest look very dark, and so on. Blue the same. White makes everything look the same because none of those caps are white. And infrared a little bit brighter than what you would see with white. But it's a good picture image to show you kind of how different colors light affect different color targets. And next, another thing that's also very important, so I'm showing here is a picture of the top of a small, say, pint of ice cream, German brand of ice cream. And then what I'm showing is how does this look with different types of light, with filters and without filters. So I'm showing an image of a red light. The top of it looks very good with a polarizing filter. What the polarizing filter does is it filters out a lot of the other light that's going on because it makes it look very reflective and very glossy, like I have in the second picture. When that polarizing light is not on, you can barely read the top of the ice cream. When we go to infrared, just to give the audience an idea of how important mounting angle is if we hit it with infrared direct on, it's kind of washed out. You can't really see it very much. But if I take it indirect just on an angle, everything looks very, very clear. So it's important to understand how these filters work, how to get an angle, because setting this up and getting a good image is the start of doing a successful application. And then last, all that I'm showing is to bring it back to IFM here is just the entire product line of what we're offering. So it's a 1280 by 960 pixel resolution. If you multiply them together, you get to 1.2 million, so 1.2 megapixel. All of the lights that we use to illuminate and look at a part are internal, so there's nothing external to screw onto. We do have external lights, which are sometimes required if you need to see a big area, like for example, a pallet that you would typically see in a logistics center or something like that. And just showing the different types of communications, whether it's Ethernet or Profinet. We have 3 standard lenses that we use. So you buy the camera by a standard lens. We call a telephoto, or really a zoomed in lens, or a wide angle lens. So again, these different lenses you pick in order to optimize your application. If you have a small part, but you need to be very far for whatever reason, you would want what we call a telephoto or narrow lens, so we could focus on something small, or a wide angle if you have to be close and you have a very large part in front of you. So there's some options here, but this is what our product line looks like. I was going to go ahead and let's do an application together. So what we're looking at now is just a simple sprocket with 15 teeth in it. On the edge of the sprocket is a tiny little chamfer that is machined into the end of it. So very common, what would happen is a customer from an industrial plant would come to us and say, I need to make sure that the sprocket is a good part, which means I need to make sure it has 15 teeth. And I also need to make sure that the ends of these teeth are not chipped off, which would make it not operate properly. So right now, right out of the box, this is what our image looks like. And what I wanted to do together is let's do this together. So right away, we have a certain kind of exposure. I'll put my hand under here so you can see that we are live. And so right now, we have an exposure time of 388, but what I'm doing is I'm zooming in to the edge of my sprocket, and I can see a lot of gray and fuzzy lines. So I'm going to go ahead and bring up my exposure, which brings more light down onto the sprocket. And for those of you that can see, this gray area is getting smaller and less fuzzy. And if I go up a little bit further, we have a nice tighter black line. Now I'm zoomed in as close as I can be, but that black line looks really, really tight for us now. So I would say we're looking at a pretty good spot here. I would like to add a filter here. So we have different filters to make white pixels appear brighter and darker pixels appear darker. Now, since I have a black sprocket on a white background, I am interested in making the dark ones as dark as I can. So I can put filters over this and make it a little bit darker here. And really what I'm looking for is I'm looking for this nice black crisp line on the edges, which looks very, very good on this image all the way around. So next, I'm going to start with what I was speaking about with a pattern match or a contour detection here. So I'm bringing in first step is to use our little tool to really, and it works a lot like Microsoft Paint, to be honest. So that's kind of how it handles with your hand and your mouse. And so what I'm doing is I'm teaching the nice rounded tooth edge of my sprocket here. So everything looks good. We found it. Everything looks clear. And then I'm going to move on and say, okay, how do I check the 15er here? So right now, I just moved on to the next step, and we draw a region of interest that's as big as the scene. So now we're looking at the entire thing. Now only one tooth has appeared. And so over here, it says number of objects in the ROI. I know I'm looking for 15 teeth, so I changed 1 to 15, and we notice absolutely nothing happened. Now, the reason that happened is the orientation of this tooth has this orientation pointing to the left, let's say 9 o'clock. In our software, we are showing I only allow minus 10% to 10%. So if I move that to minus 180 to 180, now I'm looking at an entire circle, and all of my sprockets, all 15 of my teeth just turned green. So that's step 1 in the application. We want to make sure that there are 15 here. And if I show you in my results here, it'll tell you object starts at 0 and then ends at 14 with green across the board. So that's showing we successfully just detected 15 teeth. Now, step 2 I wanted to show you of the application is let's make sure that the ends of these teeth are not chipped and that they're cut correctly. So for this one, I'm going to use the other tool that we have, which is a pixel counting tool, or in the industry, sometimes known as a blob tool. So those of you who can't see, the edges of these sprockets are very, very dark. And I'll call it the flat surface of the sprocket is much lighter. So how pixel counting things work is now I've looked at my part, and then we have, it's called a histogram, which is a very fancy word for just a slider bar from black to all the way white. So we have to tell the camera which pixels are we interested in. And as mentioned before, the ends of these are very black, so we really are interested in the black pixels. So I can move my slider bar around to say I'm only interested in black pixels. And now that the camera is done finding it, we get a nice blue shape all around the end of this, and we're able to see this chamfer on the end. And so now I want to move forward, and I don't want to look at the whole part this time. Let's say I'm interested in exactly what sprocket is broken or chipped off. So I can create a little region of interest around the one that we did together. And then I can look at, say, okay, this has an area of about 1700 pixels. So if I were to zoom in, there's 1700 tiny little pixels on the end of the sprocket, which means it's a good part. So if I want to look at others, I just click on adding new regions of interest. It's very easy to go around. I won't do all of them, but you get
You're
the
basically
idea.
copying the tool and just moving it to the next tooth.
Yes, yeah, correct. And so now that we've done that, you can see here's all of our little areas.
Yeah.
Yep. Yep. So here's all of our little areas. And then let's say one of these teeth is chipped. And I'll do my best here. Okay,
Yeah.
so I blocked one of them, but I didn't block all of it. And let's say that's broken off. That specific one went from 1700 to 800. And so what I can do in my tool here is I can say, okay, what's the lowest object area that I'll allow to be a good part? I'm blocking it at 800. If I change the minimum to 1200, then we still see that there is some of that machine, some of that flat there, but it's not enough. So now we're actually failing it. So if we look at our results again, we see that one of the regions of interest has failed and the rest pass. And so now at this point, we actually know a customer next step could be, well, I know where region of interest 0 is. So now they know specifically exactly which one is failing. And so a lot of times manufacturing plant would be interested over time. Is it always the same one? Is it always the same spot? Because if that answer is yes, then you probably have something that you need to fix further upstream in order to prevent this from happening even further. And
so ROI is region of interest.
Yes, that's correct.
Okay, so that's each tool is labeled ROI 0, 1, 2, 3, 4, and so on. Okay.
Correct. And you can go 0 to 63. So you can do as many of those.
Now I want to ask you a question. Usually the part's not always in exactly the same place. Are we able to adjust for that?
Yes. So what I did so that's a great question. And what it is known as in the camera world is an anchor function. And so what that actually means, I have it here. You can see it for those that can see it. But what that actually does is this part in reality, Shawn, you're correct. This could be spun in any number of directions. And so we want to make sure that our tools, that our regions of interest are following the ends of these teeth because it could spin in any direction radially in a circle. And so what the anchor tool function would do is it grabs onto a unique piece of geometry and it only looks for that. And so as this part moves or spins or rotates, every tool that we created ourselves would rotate with it, and we would accurately read the part.
Nice.
And so just to show you the overall, so right now we're in our test mode. So right now the camera is, both things have to be true. There have to be 15 teeth, and also the area on the ends of our sprocket has to also be true. So now my screwdriver is still blocking one of them. So we are doing nothing but failing it over and over again. And as soon as I remove it, we now have a good sprocket, and now we will just continuously be passing this part as a good part.
Now this is just constantly going and doing the readings and checking it. Would you typically have a trigger to trigger it?
Yeah, that's a good question. So at the very beginning, when we're setting up our images and I was making things darker and lighter, that's where we would set up our trigger. Right now, yes, I have it in a continuous trigger where it's going to keep triggering as fast as it can. And right now, our program is a quarter second, but in reality, in most customer cases, they're either going to trigger it with a PLC, so the PLC will know when it needs an inspection from the camera, or also a lot of people use an external sensor. So it's just a photo eye or a proc switch or something like that that's positioned in just the right spot so that the camera takes the picture at the right time.
Now I want to talk too about, and I don't want to jump ahead, but I want to talk about the outputs because you're showing outputs here and one of them is on. So can you tell us a little bit about that?
Yes. So in terms of this, you really, when you're solving these applications, you can find yourself in a lot of different situations. So like, for example, you can go to, it happened to me several times, you go to a big automotive plant in Michigan, and they've had machines that have been running for decades of time, and you come in and they need a little pokey-yoke solution, and they
Hmm.
could tell you and say, hey, I only have digital inputs available. So
Mm.
we have the ability, we have a tiny little mini PLC built in, so we can take our parameters and say, hey, output 4 is always a good part, output 5 is always a bad part. That's one
Oh,
way
all
of
right.
doing it. Another common way of doing it is a lot of programmers just say, "Hey, give me all the information over Ethernet." And so how that would actually look for those that can see, there's a lot of numbers and semicolons, but that's what the Ethernet string would actually look like. So you can look at that and really look at a map or a lookup table to say, okay, here's the parameters of the situation that's going on for me. So either you can look at it over Ethernet, or we have a little mini PLC inside, and you could just tie things to digital outputs. The customer really has a lot of options.
Now, I saw somewhere where it said Profinet. I saw somewhere else where it said Ethernet IP. Are those your major options, or are there other options as well?
Yeah, that's our major option. So Profinet, again, being a German company, is very common with the Siemens PLCs in the
Hmm.
European Union, and of course the Ethernet IP over here with the Allen Bradley PLCs. But that's the two main ones.
Okay, excellent. And so if you want to just do digital, you could do that too, which is excellent.
Yes, yeah, correct. So just to show real quick, we have something that's unique with our camera platforms, what we call the logic layer, but what it really is a mini PLC.
Hmm.
So what I can do is I'm bringing in, we programmed two things together. We did the 15 contours for the teeth, and we also did the quality of the teeth on the edge. So I can bring in blocks and do simple tasks like compare the area of one versus some number. So remember when we put it in the software and we said,
Hmm.
hey, anything under 1,000 pixels is bad. So we could also do something like that here. And what I'm showing is here's our area coming in on region of interest 0.
Hmm.
So just one of them teeth, and we can see that number is 1,700 again, and I can put it against 1,000. And then from there, I can say, okay, if B is greater than A or if A is greater than B, then trigger this output.
Wow, that looks
Uh,
pretty powerful. Yeah.
Yeah, as an example, this can grow depending upon what people are doing. It can grow to quite big, but what customers have found is this gives them a very safe and flexible environment to kind of do their work. Some people like to do all the work in the PLC, and that's completely fine. But some people like to offboard a little bit, and we've found with this user interface, really, a lot of people have found that this is easier to use, so they'll do kind of any of that next level logic in the camera, and then the camera can just report something more simple to the PLC.
Yeah, and it makes it PLC independent. So if you put the program in here and control your outputs based on that, then it doesn't matter what PLC you're talking to.
Yeah,
Very
it
interesting.
also it helps from a troubleshooting standpoint as well. So
Yeah.
if there's no question, if you come in and customers typically will just say, hey, this isn't working, or I'm failing parts that I think I shouldn't. If you put all of the work in the camera, then when someone like myself or a support team comes in, there's no guessing of, well, what is the PLC doing that I don't
Yep.
know? So that it just puts really the customer in a more comfortable situation, so we can come in and we understand, kind of where's our sandbox, and we don't have to do any kind of guesswork that something else is doing something that we're not expecting.
And you can set it up all on your desk. You're more likely, if you're buying this camera, to have it on your desk than you would to have a whole control system and PLC and all that.
That's very true. Yes. So that's what I had so far for this quick demonstration. Again, what I'm trying to do is expose people to a new software. I wanted to cover what camera hardware is because I think it's always important to understand how things work before we try and go ahead and dive in and start to use it. If you know how it works, then you will have much better and faster success when you get to the end. But also really some little tricks to do some interesting things. And yeah, it's a very fun world. of applications to try and tackle. No two applications are the same. They are all different from the next one behind it. And some of my favorite parts is, just a little bit of clever thinking, some knowledge of basics and of how things work. And you really are free. There could be 10 ways to get to a good end, and all of them are great as long as it's working and showing the right part. There's no approach that's better than the next as long as you get to the right result.
Yeah, now for the audio only audience, could you share the exact model number that you're using and the name of the software and tell us, like, do you get the software for free if you buy the hardware, or do you have to buy the software? Could you run through those for us?
Yeah, good question. So what I'm showing today is the part number from us is an O2D 520. O meaning optical, 2D is a 2D camera, and just a 520 represents an infrared camera with a standard lens on it. Our software is called the IFM Vision Assistant, and the software supports than just their 2D camera. It supports we have a barcode reader, a 3D camera, an outdoor 3D camera, lots of other things. The next step
Oh,
for us is for going on AGVs. So these are just driverless vehicles. And so
mhm.
what these mobile robots need to know is they need eyes. They need to know, is that a person to walk by? Is that a shelf or a wall I'm going to run into? And then they can handle it accordingly. All of this software is a free download on our website. So you only need to log in and have a simple login, and all of the software is free. The only price is the hardware. All of our list prices are on or public information on our website. List price for the camera starts at $1,700.
That's great. And this isn't just not a code reader. This is a full 2D camera for inspection. So as we've seen, as you've gone through, because there's a big difference between just a code reader and a full-blown 2D camera. So and I think the way you went through that in your example was extremely well done. Folks, if you're listening and you're interested, I would definitely check out the video version of the show, because I really think Chad did a great job going through it and really chose some great examples. And I know we went through this quickly, but if you rewatch it, I think you'll see a lot of these little things stand out on the easy use of this. So Chad, is there anything else you wanted to cover? That was excellent.
Yeah, no, this is great, Shawn. I'm happy to discuss these technologies. I've always been a fan of understanding how things work, and then I always thought live demonstrations were the most interesting to show people what's possible.
Now, if some of our viewers are really interested in this and want to contact IFM to learn more about it, who would they contact?
Okay, so we have a phone number on the website. We have everything on the website if you want to contact us. So we have a very, very strong customer service team. And so if you call the 800 number that you'll see on the web, you will see one of our customer support engineers that are actually downstairs and where I'm seated right now. And what they do all day, every day is they have every single one of our products connected. And Teams or any other kind of view share is a beautiful thing. So we're doing this all the time so we can screen share and show people what to do or help them with their question or help them with integration. So all of that stuff is available, and we spend a lot of efforts as a company to make sure that anyone who is interested can get what they want as fast as they can.
So give them a call. To just go to the website, get the information you need, give them a call. They have experts waiting on standby to answer your questions. I know when I've called, they've always been super helpful. So I can totally endorse that. But in any case, Chad, I really want to thank you for taking the time out of your busy schedule to put this demo together, to put the presentation together, to come on and share this information with us. I really enjoyed it. And again, I just want to thank you for coming on.
Yeah, Shawn, I thank you very much for the opportunity. It was a lot of fun for me.
Well, I hope you enjoyed that episode, and I want to thank Chad for taking time out of his busy schedule to come on the show and bring us all up to speed on IFM's 2D vision cameras. And I really thought the application example he gave at the end there was really well done. With that said, if you did enjoy this episode, please consider giving us a like and a sub. And if you want to follow me or keep in touch, you can do so over at automation.locals.com. You'll also find all of my PLC, HMI, and SCADA courses at theautomationschool.com. And with that, I want to wish you all a very happy, safe, and healthy week. And until next time, my friends, peace.